So in part C of this question, we are given this graph showing the variation of time t against this with the speed of the ball at the instant it hits the ground from the start when we have launched it. We're asked to state the value of the area under the curve. And well, we know from the previous part A that the ball was released from 28 meters above the ground, and in fact the area under a velocity time graph is going to be our displacement, as velocity times time is displacement. So that is one way to think about it. And then in part 2 we need to determine K. So we know that K was in the equation F air resistance is equal to kV squared. So we also know that at the terminal speed, this force is equal to the gravitational force, which is mg. So when we are at the terminal speed, right, this velocity is constantly changing, but at the terminal speed, when the velocity is no longer changing, this equation is correct. And in fact, we do know the terminal speed because we can read off the graph that it approaches this constant value of about 9.5 meters per second squared. So all we need to do here is rearrange for k. It's going to be mg over v squared. So we know the mass was 2.7 grams. So 2.7 times 10 to the minus 3 times 9.81 divided by the terminal speed of 9.5 squared will give us a final answer of 2.93 times 10 to the minus 4. And then we know the units again from the previous part is kilogram per meter. And then in part 3, we're asked to on this axis sketch the variation of the magnitude of the resultant force against time. We don't need to include any numbers. So here what we need to make sure that for 1 mark we get the general shape of the graph correct. We need to know that at the start is going to start off some value that is mg. As at the start we have no air resistive force, as because at the start we have 0 speed, so kv squared is 0. We just have mg. And we know that at the end of our motion, this resultant force has to approach 0, because at the terminal speed, the net force will approach 0 as we have no acceleration, so we reach the terminal speed. So we could draw some graph like this. The general shape is not so important in this question, as according to the Mark scheme, it's only important that at the start we start from mg, and at the end we approach 0 asymptotically. And yes. And then in part 4, we need to determine the average force exerted or dissipated by the air resistive force. So what we need to see is like how much energy did the air resistive force take away from the ball. And we can see how long that took. We know that the total motion was about 3.6 seconds. So with energy over time, we will be able to determine the power of the air resistive force. So the energy that we lost at the start, we have potential energy, and at the end we had kinetic energy. So if we subtract these two, we will find how much energy we lost. That would just be mgh minus 1/2 m, and then v squared is going to be our terminal speed, as we no longer the highest speed we reach is 9.5 meters per second squared. So if we plug in all the numbers here, we get this is 0.620 joules. And then as we discussed, power is simply energy over time. So the air resistive force dissipated an energy of 0.62 joules in a time of 3.6 seconds. And this is equal to 0.172 watts.